Hello, everybody. Welcome to the second webinar of the CIRCULAIR project. The second webinar will be a deep dive on hydrothermal liquefaction and its coupling with wet oxidation of the process water that results from hydrothermal liquefaction. And as in all webinars of this series, we have two speakers. First, we have Patrick Biller from the CIRCULAIR project, and Patrick is assistant professor at Aarhus University in Denmark, and he leads the hydrothermal processing research group at Aarhus University. Second speaker is Juliano Souza dos Passos of PNNL in Washington State, USA, and Juliano is platform lead for hydrothermal processes at PNNL. So quite similar names of the institutions. They also do quite similar research as well. One difference is that, so I did research that both labs are a little bit less than 8,000 kilometers apart. So for Juliano, it's early morning. Patrick is sitting in Denmark. Still, it's a little bit of a family meeting. So Juliano was doing his PhD in Patrick's group at the time where I coordinated projects together with them. And so when I now say maybe these groups may be the most distinguished one on this particular topic on both sides of the Atlantic, I think I can do this. I may be a little bit biased, but this is my statement. So we start with Patrick, and before Patrick starts with his presentation, I want to make a little bit of advertisement for upcoming webinars. So CIRCULAIR will organize more webinars on various subjects of the project. Likely the next one will be on HTL biocrude upgrading, and you can also check the website for other workshop and events. For today, during the two presentations, you can ask questions in the chat. I will collect these questions and package them and ask them to the speakers afterwards, and then towards the end we may open then also the floor for questions from the audience. And just to let you know, we are also recording the webinar, and we are planning to make this available online afterwards. So Patrick, the floor is yours.
Thank you very much for the introduction, Valentin. Yes, so I'm going to be talking about the integration of the HTL process with this wet oxidation process, with the aim of achieving an autothermal process. So just as a reminder, I'd like to quickly remind you on the CIRCULAIR project. The overall scheme is shown here. So the aim in the CIRCULAIR project is to produce sustainable jet fuel from highly abundant agricultural feedstocks, namely manure and straw. And then they go into this combined HTL wet oxidation process, where the oil is then upgraded by Aarhus University and Topsø, and also with support from ENI, to primarily jet fuel. We're also looking at the side products, so particularly the hydrochar is going underground for carbon sequestration and fertilization, but even with Hohenheim. And then we're also looking at VFA recovery and ammonia recovery from Madrid. And the central part here is the HTL wet oxidation integrated process, which has the aim of cleaning the wastewater, providing heat for the HTL, but also the CO2 from the combined process can be used for methanol synthesis. And conceptually, if you're running an electrolysis process, produce hydrogen for the upgrading and for the methanol, you could also use the oxygen as the oxidant for the oxidation process. So the concept that we're targeting, so on the left-hand side here, you basically have standalone hydrothermal liquefaction of an example carbon balance, which is where you start with 1,000 units of carbon in the straw. You go via HTL, 400 units of carbon would be going to the biocrude, but you can see that 365 units of carbon are actually lost into the aqueous phase. And this is where the wet oxidation process can use these 364 units of carbon, oxidize them, primarily producing heat, and then also producing CO2 and some volatile fatty acids. This is all carbon-based. And then the concept involves utilizing the CO2 together with the CO2 from the HTL process to produce methanol. So the idea is that we have a near complete biomass utilization by using all of the side streams. And then also another aim is to really increase this kerosene fraction to make jet fuel. And with the ultimate goal of actually achieving carbon negative jet fuel production by sequestering some of the solids underground and basically plugging all carbon losses so that they are minimized. So also today's seminar is focused around the wet oxidation process. So just briefly, this is a relatively old technology used for cleaning high COD wastewater, where the concept is essentially you have a feed pump pumping your wastewater, combining it with compressed air, heating it up in a heat exchanger, and then the oxidation takes place between the organics and the oxidant. This is an exothermic process, creating more heat. And then after the oxidation, it's cooled down, the pressure is released, and you separate your treated water from the off gas. And conceptually, essentially, you have your organics and the wastewater. They are oxidized to CO2 and water. But additionally, there is an intermediate step, an intermediate product often formed, which is actually acetic acid, which then can also be oxidized to CO2 and water, but it requires quite harsh conditions. So this is often found as an intermediate product. So this is the wet oxidation process. And the idea of HTL wet oxidation integration, I'm going to try and explain here. So it all is based on that the wet oxidation process is exothermic and produces excess heat. The idea is that we can use this to provide the heat needed for the HTL. So on the left side of this diagram in green, you basically have a normal HTL process where you have a biomass slurry at ambient temperature. It's heated through a heat exchanger, which is heated by the HTL product to around 280 degrees. Then it would go in your HTL reactor, which we are operating at 325 degrees here. And then it'll be cooled down by heating the influent slurry. And then your HTL reaction is finished. And you would separate your biocrude oil, your CO2 gas, and your hydrochar in a separation here, leaving you with the dirty process water, very high in COD, which then goes into the wet oxidation process. And in the wet oxidation process, again, you have a heat exchanger to heat up your process water to, let's say, around 280, 290. And then you add the oxidant. And this is then introduces this exothermic oxidation reaction. And that will then increase the temperature of your process water to around 350. And this heat, this 350 degrees, can then be transferred by a heat exchanger between the wet oxidation side and the HTL side, which means that the HTL, these 280 degrees, can then be increased to the final HTL reaction temperature of 325. So typically you would have done this with a trim heater in a normal HTL reactor, but in the integrated process, the idea is that you have a heat exchanger where the trim heater is replaced with the heat exchanger, which provides the heat from the wet oxidation over to there. After this, you have the heat exchanger where you are heating the influent process water. And finally, you have your treated water and your CO2. So that's the core idea of this thermal integration of these two processes. So first, we try to model this process to see if it's theoretically possible to run autothermally, which would mean providing all the heat for both processes from the exothermicity. So first, we did a heat exchanger layout and a pinch point analysis to get an optimum heat exchanger network, which is shown here in this diagram. Then we did an Aspen wet oxidation model to model the outlet wet oxidation and the amount of heat released from the oxidation of these organic compounds based on the kinetics that are of known compounds that were found in literature. Then finally, we did a MATLAB optimization code for the entire process integration and modeling all the temperatures that are at these different points in the diagram. The model assumed 1 kilogram per second biomass slurry input so industrial scale. We used pure oxygen for this modeling, and so we included the 3 different production technologies for oxygen: electrolysis, pressure swing absorption, membrane separation. And we also included the energy required for treating the wastewater after either HTL standalone or HTL combined with wet oxidation. The aim was to find the optimal configuration to reduce the overall energy consumption and achieve autothermal operation. So the modeling results, this here shows the HTL standalone system, where you essentially, we modeled 3 different reaction temperatures and 3 different times, so 300, 325, and 350 degrees, 10, 20, and 30 minutes of reaction time. And you can see that the total energy consumption is between 230 and 260 kilowatts for this system that we modeled for the standalone. And now I'm going to jump straight to the combined process. So here we're performing HTL again at these different reaction temperatures and times, but and the wet oxidation at 350. And what you can see is that the trim heaters that are usually used to bring your reactants up to the reaction temperature in the wet oxidation reactor, the energy consumption is 0, meaning they are not needed at all. So all these top 4 lines, they're all heat exchangers. So these duties, these kilowatts here, they're for free. There's no electrical heat provided. The only heat we need to provide is actually for heat losses of the HTL reactor itself. So the total energy consumption drops from 235 kilowatts to around 2 kilowatts for the heating only. It's only for heating. But essentially, this shows that autothermal operation is possible for the majority of combinations of HTL wet oxidation, but not if HTL is run at the same temperature as wet oxidation, namely 350 degrees, because then there's no temperature difference to transfer the heat needed for the HTL reaction. So if we now look at the total energy consumption of the HTL standalone process, here you have the heating makes up the bulk, 60%, and then you have the wastewater treatment on 30%, and then a little bit for the pumping. So total 455 kilowatts. The combined ones, you have 3 cakes because there's 3 different oxygen production technologies: pressure swing absorption, electrolysis, and membrane separation to produce the oxygen. You can now see that the total energy consumption is around half. And now the majority of the cake is made of this blue one, which is actually the energy consumption for the oxygen production and the oxygen compression. But the overall energy consumption is around half of that from the standalone process. So you can see that the oxygen production takes a lot of energy. So you might think, why not just use air? And that is a very valid question. So on these different blue bars here, the pressure swing absorption here, 15% of this blue area is for the compression and the rest for production. And these vary a little bit between the different production technologies. For example, electrolysis is quite energy intensive. So only 5% of this would be for compression and the rest for production, also because it comes out of the electrolyzer at elevated pressure. So if you would use air, it would use about 65 kilowatts versus the 85 kilowatts used in the pressure swing absorption. So about a 20% reduction in this blue area. So that is entirely a possibility worth thinking about, and we'll get to that in a minute as well. But first, another energy comparison of these integrated and non-integrated processes is something called the energy return on investment. So here we compare the energy produced, which is the mass flow of biocrude times the heating value of the biocrude, compare it to the energy need for pumping, heating, and wastewater treatment. And that then gives you a ratio of how much energy is produced compared to how much is consumed in the process. And the green ones here are for HTL standalone, meaning you produce around 3 units of energy for every unit of energy you have to invest in running the process. So that is fairly okay. And if we look at the ROE of the combined process, you can see that we have to add the oxygen production and compression costs to this, as well as additional pumping for the wet oxidation process. But regardless, you can see the ROE numbers are increasing quite significant compared to the standalone, because we've saved so much on the heating despite additional energy for the compression and oxygen production. You can also see that it makes a huge difference which oxygen production technology we use. And again, you could ask, should we be using air versus oxygen? And this is something I'm going to talk about in the next couple of slides. We did an additional study on a continuous system where we tried to mimic pure oxygen with providing hydrogen peroxide, which then decomposes to oxygen and water, and then simulating pure oxygen addition. And well, basically, you have to consider that air is a lot of nitrogen. So when you're compressing it, you have to compress a much larger amount of volume compared to pure oxygen. So this is the disadvantage for sure, but you don't have the production cost disadvantage of pure oxygen. And then there's also the question about the solubility of nitrogen. Basically, oxygen and CO2 solubility at redox conditions are complex, but quite high, almost complete compared to nitrogen, which will make a separate gas phase on top of your water phase or mix in between your water phase. And this can mean that water, the equilibrium between vapor and liquid will change, meaning that more water will evaporate, which will consume energy lower than the heat release of your system. So there, the nitrogen is a big disadvantage. An advantage of using pure oxygen is also that you actually have higher CO2 removal slightly than using air equivalent, as you can see in this figure where we tested air versus H2O2. In terms of the other experimental parameters that are important, so nitrogen, we aim to recover as ammonium after the wet oxidation process. These first two figures show with air, and the final one with hydrogen peroxide simulating oxygen. You can see that the blue ammonium selectivity in the residual nitrogen drops from 80 to around 60%, so meaning oxygen is disadvantageous for this. We don't know quite why. Another one that is interesting is the recovery of acetic acid in the post-wet oxidation water, and here we don't see a difference between air and hydrogen peroxide. But then there's also back to this diagram of the CO2 recovery. So if we're thinking about the CO2 recovery, we're producing a lot of CO2, so sequestration would be quite interesting. Then this can be quite interesting to evaluate. We know that the HTL gas is around 95% CO2. And here these two tables compare hydrogen peroxide simulating oxygen versus air. And you can see if we provide substoichiometric amounts of oxygen, then we end up with 97% CO2 and hardly any unconsumed oxygen. If we do the same with air, we end up with 18% CO2 and a lot of nitrogen from the air. So then this would also be advantageous to using pure oxygen. So to summarize the experimental results, basically the CO2 removal is a function of time and temperature. So typically we reach around 80% of realistic process conditions. The ammonium is also converted quite efficiently, reaching about 80% selectivity. VFA is also around 80% selectivity with high acetic acid. And if we run substoichiometric oxygen supply, we can reach 97% CO2. So then there's one more complication that I'd briefly like to talk about. That's about the air injection or oxygen injection location. So if you think about a reactor with a heat exchanger, trim heater, main reactor, heat exchanger, cooler, outlet, you'll have a temperature profile looking like this. And we tested initially two air injection locations. One was after the heat exchanger, and we noticed that there was a drop of temperature due to the introduction of cold air, which is of course not great if you want to integrate heat, and also probably due to vaporization. If we do it before the heat exchanger, then all the exothermicity takes place before in the heat exchanger, where you're actually supposed to be exchanging heat with the products. So it is also not ideal. So we investigated this in a little bit more detail by changing the air injection locations from before the heat exchanger to after the heat exchanger. And then we also tried preheating the air by basically laying the air pipe on the trim heater to preheat the air. And then we also tried to add some check valves because we noticed the air was going backwards in the reactor, reducing the temperature backwards. Long story short, the best we found was preheated air actually had a positive effect. So, but this is actually quite a complex system, and there's also some experimental uncertainty, but you could definitely see a difference. But this is something that we're now on the technical implementation will be investigating further on our new demonstration integrated reactor. So I'll get to that now in the next couple of slides. So I'll remind you of this overall concept from earlier, and here you can see how we're going to implement this technically in the drawing, but also in the actual physical picture. So the wet oxidation heat exchanger is here on the floor, basically tube in tube, 4 times 5 meters tube in tube heat exchanger, because we don't have any solids, they can be quite narrow. Then we have on the top a heat exchanger for only HTL, and then we have 2 heat exchangers in the middle, which basically exchange, one side is HTL and one side is wet oxidation, exchanging the heat between them. And the whole system has a capacity of around 120 kilos of slurry an hour, the equivalent on the wet oxidation. So this is the picture of these heat exchangers. So you'd have a hot and a cold and a hot and a cold and a hot and a cold. And in the top one, it would only be HTL, where I have just hot HTL, cold HTL. And these other 2, you have HTL in 3 pipes and wet oxidation in 3 pipes, transferring the heat from the HTL to the wet oxidation. We also have the option of adding heating to these so that we can run HTL and wet oxidation independently without each other. And then the final thing that is on the air injection or oxygen injection, we've added some options so we can pump H2O2 solutions into the reactor. We have gas boosters to provide compressed air, and then we can measure, of course, all of this. And then this is, of course, a bit too much detail, but essentially we have 2 different locations where we can then add the oxidant to optimize this and avoid these effects, also with preheated air and oxygen. So to summarize, autothermal HTL wet oxidation integration is definitely theoretically possible. As the modeling has showed, it's actually quite easy in terms of how much heat is produced. In addition, it has added benefits by obviously reducing COD by about 80%. Ammonia, VFA, and CO2 are produced, which are interesting for downstream recovery and utilization. But you have a penalty of increased capex because essentially you need 2 reactors and more compressors and things like this. Overall, the HTL wet oxidation energy consumption is around half compared to that of a HTL standalone system. The compression costs are significant, around 60% of the HTL wet oxidation system, while it's 90% heating for the standalone. Oxygen is superior in terms of various aspects, but supply costs need to be considered, so it can be quite costly. The optimal injection of the oxidant is something that is quite tricky and we need to be working on in the coming months. So the implementation, you saw some pictures of the combined reactor, is close to be finalized, but we still, the demonstration of the autothermal operation is still outstanding. So that was all for me today. So thank you very much. And yes, I'll pass over to Tino.
Yeah, thank you, Patrick. I mean, I will directly pass over to Juliano. So Juliano, please share your slide. And maybe just a short reminder to the audience. There is the option to ask questions in the chat, I think, to both presentations, and afterwards we will then have this question and answer session. So please take the opportunity. Okay, Juliano.
Okay, thank you very much. Thanks, Patrick. So after Patrick's presentation was a very good view on the integration of wet oxidation and hydrothermal liquefaction, I would like to talk a little bit more about wet oxidation and reactor considerations for the design of this unit and how to actually make it as efficient as possible so that it can be integrated with hydrothermal liquefaction. So the classic hydrothermal, this classic wet oxidation is it is a hydrothermal process. It takes complex molecules on the COD side, reacts with oxygen, and then you get CO2, water, ammonia if you have nitrogen in your complex molecules in the beginning, and then you have small molecules. Even though I'm saying here that it is complex molecules on the left side and small molecules on the right side, one of the main applications industrially for wet oxidation is the oxidation of phenols. And that's because phenols are very difficult to treat in a wastewater treatment facility. And therefore, wet oxidation comes as an efficient process to actually reduce the amount of phenols, create different molecules that can then be treated. So it's an efficient process for toxic wastes. One of the reactants is widely available. Well, it's oxygen from air, basically. So even though the production of pure oxygen is very costly, the availability is there. It's widely used in industry, and it's a relatively simple concept. There's no catalyst, there's no additives that you have to put in. It's relatively simple to actually make a liquid and a gas reaction to a certain extent, and we'll talk more about that. So it's difficult to attain autothermal operation, and I think this is something I would like to highlight, is that typically that's not even the target for the people that do wet oxidation in industry. And you'll see what are the ranges of temperatures. They're actually trying to depollute the water or to remove the toxicity. Most of these companies that sell wet oxidation reactors, they are not trying to get autothermal operation. It's a nice to have. It's not a must have for the business model, because the business model is based on the treatment of polluted waters rather than the attaining energy efficiency at all. So gas pressurization and costs are significant, as Patrick was mentioning. That's often prohibitive even. Long residence times are needed, so something along the lines from more than 30 minutes all the way to 90 minutes or something, and quite often special metallurgy because of the oxidant nature. So a very different hydrothermal process. If we compare it to hydrothermal liquefaction, which is a reductive process, this is an oxidant process. This requires the intimate contact between the gas and the liquid phase, which is something that everyone has to consider when looking at the reactor design itself. So now let's talk about the properties of the reactor, starting with temperature and pressure. So on the left side here, what we have is the pressure per temperature saturation pressure of water. So this curve here, most of you guys that work with hydrothermal liquefaction are quite familiar with it. So if we are talking about temperature of around 300 degrees Celsius, we're talking about pressure that above 80 bar or so that you are that all your water is in liquid phase and you don't have any evaporation. On the right side here, there's a graph showing solubility of oxygen in grams per oxygen per liter of water versus the oxygen partial pressure. So you can see here, if we are at around, again, 315 degrees here, and we're talking about an oxygen partial pressure of 20 bar, so 2 megapascal, our solubility is about 3 grams per liter or so of oxygen. And I added this unit as grams of oxygen per liter of water on purpose because that's the measurement of COD. The COD of water typically going a little higher than this makes difficult for you to attain a condition where your oxidant is delivered to the liquid part of your reaction at the same rate that it needs to be consumed. Therefore, your process starts to be not only mass transfer limited, but also limited by the proper solubility of the oxygen. The oxygen cannot even be there together with the organics to be oxidizing in the liquid part. And of course, 20 bar of oxygen is 95 bar of air. So if you do wet air oxidation, if you use air in your system, you have to account for a much larger pressure. So if you look on the left side and you are again at 300 degrees Celsius, you have 80 bar of natural like pressure, saturation pressure of water. You have to add 20 bar for oxygen, but you have to add 95 bar for air for you to get the same pressure for oxygen on the other side in the thin equilibrium, looking like this. Quite a lot of our simulations are happening right now for us to understand better how to handle these, and of course Costas from Aarhus University as well has published just recently a very good paper on that, short paper on solubility of oxygen for these systems. So typical wet oxidation happens around here. It's from 175 to 250 degrees Celsius. And what we are trying to do is different. Is on the right side. It's from 300 degrees to 360 degrees maybe. This would be way better for us to be able to integrate with hydrothermal liquefaction. The typical wet oxidation, again, doesn't aim at the autothermal integration as we are trying to do here. So we're talking about pressure and temperature again. I just put this simple figure here showing on the left side you have a system of liquid and gas. If you increase the pressure, you reduce the size of the bubbles, but if you increase the temperature, you increase the size of the bubbles. So that's maybe one of the things that that everyone has to consider when designing a reactor: how to inject the oxidant, so that your dispersion of oxygen in your surface area actually allows for the oxygen to be delivered where the organics are and to be able to make an efficient process. And of course, the isotherms of solubility on the right side of oxygen, they show exactly what we were talking about. That so if you want some solubility, let's say curve number 3 here is at 350. Your starting pressure is already in the 170 bar or so. That's because the pressure of water, so the saturation pressure of water is this one, and then you have to increase quite a bit of pressure to actually attain good solubility. And even when you do that in controlled environment, it's actually difficult to attain the full delivery of the oxygen. There's a good paper that shows this video here, and hope you guys can see the video on the right side. This is just a simple phenol wet oxidation. You get phenol and you put together with oxygen in a bioreactor. You heat up to a certain temperature, in this case 300 degrees Celsius, and then when you get there, the headspace of your reactor is oxygen, and then you start the mixing with a proper stirrer that delivers quite a lot of gas to the liquid phase. And you can see in the beginning of the video here, it goes totally dark first, and then it starts to clear up as it is doing now. And it starts to clear more and more up. The reference end is here below, so if you guys want to take a look at the full video and the full data set on this one, it's quite interesting for us to think that even in a very, very controlled environment with basically full dispersion of oxygen in the liquid part, you still get quite a lot of complex molecules. So basically in seconds after you start the wet oxidation process, complex molecules appear from phenol. So in the beginning you have only phenol, which is the small peak on the left side here actually. And then after seconds you have this myriad of compounds here, which are basically showing that when you start a radical reaction with oxygen, instead of the organic radical created after the first interaction with oxygen, going towards another oxidation step, reacting with oxygen again, it actually stabilizes by reacting with another organic compound. And that's very limiting for the wet oxidation itself. In the case of industrial wet oxidation, where you're not targeting the autothermal or very efficient process, you just want to depollute your water. In practice, what you're doing is the wet oxidation of the right side of the complex molecules that emerge after the first partial oxidation reactions. So using this type of stirrer here, it's possible to deliver oxygen in a very reliable way in the liquid phase. So if you are in a stirred tank, basically this type of stirrer gets the oxygen from the headspace and delivers all the way into liquid, which is very interesting, but still you have this type of behavior. In our measurements for hydrothermal liquefaction waters, it's hard to see because, I mean, hydrothermal liquefaction waters are already very complex. So it's very difficult for us actually to measure, but we are doing some omics measurements. So that's HRMS measurements to try to understand this type of behavior under hydrothermal liquefaction, aqueous phase, wet oxidation. So talking about air versus pure oxygen, as Patrick was saying, I think I want to add a little more on this discussion. It's basically with air, you are working with larger gas to liquid ratios, with oxygen, smaller gas liquid ratios, but higher oxygen concentration, basically meaning that your partial pressure is higher with a smaller volume of gas. So second point here, high nitrogen volumes need pressurization with air, but with oxygen, full separation production unit is required. The left side, air may operate with excess of gas in a gas liquid system, and with oxygen, it requires careful gas dispersion in a liquid gas system. And this is a very important point to consider when talking about how to implement wet oxidation. Several options for methodology. This statement here for air is so-so. At high temperature, you still need special methodology, so you need to consider this as a critical element of your design. And for oxygen, even handling on the periphery of your process, you need special methodology to handle high concentrations of oxygen. And both cases, you need to handle a high pressure gas on site, right? So talking about specifically the gas liquid system and versus liquid gas system, I have two pictures here. So the left one shows the flow properties of two-phase flow, so liquid gas in vertical pipes, and the right one on horizontal pipes. So basically what you want to do if you want to really increase the chances of getting oxygen to your liquid is work with annular flows, which are bubbles fully dispersed in the main phase. And when I'm talking about gas liquid systems versus liquid gas systems, I'm talking about this type of comparison here on the bottom right. So you have a liquid gas system, just means that there is 50% or more liquid in bulk volume at your reaction conditions. And on the right side, gas liquid system means that there's more gas to liquid in your system. And if you use air, typically that's the case that you're going to get on the right side. If you use oxygen, that's the case on the left side. So and even that is very difficult to actually measure and to investigate, because the simulations at these conditions are very difficult to be made, right? So the reactor design examples here on the left side, this is the typical wet oxidation process. This is the ZIMPRO process, actually called. It is deployed in several places. Basically, you have water, polluted water, a feed pump. You go into a heat exchanger, into sort of a trim heater, and then you go into a reactor. This is typically a tower reactor. You have a big tower with oxygen dispersion, so with gas dispersion in the bottom of the tower, and then your reaction happens upflow, right? And then you go into the heat exchanger again to recover heat and go into a depressurization stage. And then you separate your gases and your liquids in the end. Residence times in the reactor piece, 60 to 90 minutes is the typical thing. Temperature is 200 to 250 degrees, as I was talking about commercial processes. And on the right side here, it's a process that was also deployed in several places, but the ZIMPRO process is definitely more used. The wet ox process on the right side here is basically a feeding pump, heat exchanger, same as before. And then you go into a sequence of CSTRs. So a sequence of CSTRs, for everyone that's a chemical engineer here in the meeting, we already know where this is going. So a sequence of CSTRs is basically a plug flow reactor. So that's a way of doing it, with the sort of advantage that you can increase your mass transfer coefficients by having steering in each section here in this pressurized vessel. The most difficult part of this process here is that you actually have to put the mixer inside. So your couplings on the top part here they tend to be quite problematic to handle, and the reliability is a little lower. But your residence times can be cut in half as compared to the Zimpro process. So mass transfer coefficient much higher on the wet ox. Zimpro process widely used because it does not target an autothermal operation at all. So now talking about our results in vertical reactors, we just published this a month ago or something. The results are quite similar from the ones from Aarhus University. We have residence times from testing from 0.2 hours, so from minutes to all the way to 60, 75 minutes of residence time inside the reactors, and we get conversions as shown here. So on the black dots here, you have the COD reduction, and we achieve very large COD reductions for on the left side for the residence time, and on the right side we test different temperatures with long residence times. So on the right side, 70 minutes or so, as compared to the different residence times on the left. So basically, we attain very large conversions, but the residence time, it has to be very large, and our temperature, the higher, the better the conversion as well, of course. And looking at the compounds and which compounds are actually formed, it seems that it's more or less constant for quite a lot of compounds if you increase your COD reduction, so the more stringent your conditions are. And then when you get to the last 25–30% of the COD reduction, you start to consume the compounds that are still there, right? So that's the case for the groups here on the left, and for specific compounds on the right. Some compounds actually increase concentration, but then they start decreasing again around 30% missing of the COD in the end. You start to actually consume them as well. So what condition of flow are we in the vertical reactor we were talking about just now? This figure here, the ideal thing would be that we will be in a bubble flow condition, but we are not. Our best estimates is that we are in a slug flow. So that means it's a bubble of gas moving through the liquid, and there's quite a bit of backflow. So the residence time distribution doesn't look good actually for this type of reaction setup, but it's useful for us to actually understand the reactions and the products formed using this type of apparatus. So over here, we try to actually measure, because we saw in the continuous flow reactor, it was there was some limitations for our understanding. We try to replicate the experiments in batch conditions, and then trying to estimate the kinetics of wet oxidation and getting into the proper chemical kinetics measurement. But remember, it's not that simple, as I showed in the other paper here, that there is a complex reaction formation of sulfur soothe formation, right, in the beginning of the reaction. But even with this, we try to estimate the kinetics, and we managed to do a very good job using this scheme here. So this scheme here of reaction basically heavy, so that's heavy compounds, and we call them easy to oxidize. They can go either directly to CO2 or go through steps of light compounds, B and C, into CO2, or into or one from the easy to oxidize light compounds to hard to oxidize, which was basically acetic acid. And then we tried to match all the concentrations we had with different compounds measured via HPLC and GCMS, and trying to bulk everything together in the same model to try to predict these conditions. And well, the kinetics here in the bottom looks pretty good. So we started to compare with the results that we have experimentally. So we have here in the first graphs from 260 to 290 degrees Celsius, and the blue lines here is basically the D, which is CO2. So if you look at the blue line, you're more or less looking at the COD reduction. but this is CO2 concentration in the end of the process. And you can see here that it's a pretty good match for all of the compounds that we have measured all the way to 290 degrees. But when we go a little further on temperature and start to go into 300 degrees, 325, and we also have more measurements at 350 degrees, 360 degrees that I didn't include here. But basically the kinetics starts not to work. So there's a change. So the basic conclusion is that when we reach after 300 degrees Celsius, there's a kinetic regime change. And the main question that pops to mind is here on the third bullet point. Are we really measuring the chemical kinetics? We are still trying to figure that out. Is to try to make sure that we are measuring the chemical kinetics and not just a mass transfer limited process. On the second bullet here, you can see now if we compare the residence times that we are talking about, 30 minutes, 60 minutes, 90 minutes for wet oxidation, now we compare with supercritical conditions, which is another whole process. So supercritical wet oxidation exists. It is a technology, and you assume that it's a single phase. In that process, they use seconds to below 2 minutes of residence times to attain more than 95% CO2 removal. It brings its own set of disadvantages that I'm not going to go through here, but it is supercritical, and it eliminates this type of mass transfer limitations that we are talking about here on the wet oxidation. And then even in well-sealed reactors, is this what the equilibrium looks like? Is this really the chemical kinetics, or are we trying always to measure something that is limited by the mass transfer side and solubility side of oxygen? Well, in general, wet oxidation.
I think we have lost.
Deliver the
Okay, please continue. We lost you. We don't see your slide anymore, but it's the conclusion. Maybe you can do your conclusions without your slide.
Oh, sure. Okay, yeah, sure. Okay, I'm sorry about that. But so the conclusion is basically making sure that we are measuring the chemical kinetics, and if we're not measuring the chemical kinetics, that's fine as well, as long as we can actually split K, L, and A. So when we're talking about mass transfer and the area that this mass transfer happens, and high pressures on site of a hydrothermal liquefaction plant, high pressure gas handling will increase complexity in the operations. So to reduce the capex of the overall concept, it's very important for us to actually reduce the residence times that we are using on the wet oxidation plant to make sure that the process itself is more economical. So I'll try to just share a little more because I wanted to show you guys the last slide, just to acknowledge everyone in our group that is doing hard work in this area on hydrothermal liquefaction and wet oxidation. I'd like to specifically mention Huaming, Pepe, and Minso that are doing really great work in the wet oxidation part. So thank you very much.
Thank you, Juliano. Well appreciated. Also good that you share the acknowledgements as well. I think we all know that this work is not like just the two of you. It's many people involved and many people doing nice work here. Remember, there is kind of questions, the option to ask questions via the chat. Maybe we can also unmute. I see that Patrick was asking in the chat, but I consider this more like an icebreaker. I'm not going to read Patrick's question, so you can ask Juliano directly. But maybe I start. And in principle, this is all about hydrothermal liquefaction. Now we talk a lot about wet oxidation, and I think it's important to recall what Juliano has also pointed out, that one of the key things here is really the cleanup of this process water, which contains complex compounds. Some of them are difficult to handle with other processes, and this is where wet oxidation comes in and may have its benefit. Now, one question, and I would like to ask this maybe to one of you, whoever wants to answer. When you couple two things, this always comes with pros and cons. So Now with this HTL and wet oxidation, you could also have the option to run both processes, let's say in a decoupled way, maybe have some advantages with choosing process conditions, also reactor geometries or such things. So what is your feeling? Is that coupling justified, or is it causing maybe a little bit more issues than solutions?
Well, answer, Juliano, shall I? I think I'll answer. I think you're right. It complicates things, of course, quite significantly. I think wet oxidation definitely makes sense, especially when you're like in a remote area, a farm or something. It can really help, and you might even achieve a water quality that might be just about okay. But you're completely right. If you look at Juliano's slides, he showed some different reactor designs that are more specific for introducing oxygen efficiently, with some stirrers and things like this. Then what we are doing in the Circular project would probably not be quite applicable. So then it's maybe not so smart to do it. It makes it also easier if you're using oxygen. You don't have to worry about the oxygen and the oil, for example. If you have them completely separate, that would make things also a little bit easier. Yeah, I think if we can actually show that we can recover a bunch of the heat and reduce the energy consumption by, let's say, 50% for combined process, then again, it could make sense. But I think it has pros and cons. So the technical implementation is challenging, though, I would say.
I think Patrick covers very well the pros and cons here. I'd like to add that that wet oxidation for hydrothermal liquefaction may be seen as an enabler of the technology to be deployed in different spaces. I think Patrick touched just briefly on that, and I think that is a main highlight for wet oxidation. Maybe if you are not handling wet oxidation in a wastewater treatment facility where you actually have the opportunity of routing your aqueous phase towards a proper treatment of water, then you must do something with your toxic polluted water in the end of the hydrothermal liquefaction reactor. So wet oxidation comes with this advantage. Of course, the process intensification side of wet oxidation to make sure that it matches the sizes of hydrothermal liquefaction plants that are deployed that way. That is where the challenge lies, and that is still to be developed. And there's work to be done there on how to actually implement that and how to do. I think the efforts from Aarhus University making a pilot plant that actually represents both processes together, it's actually what we need. Because without that type of setup for you to try the flow conditions that are more optimal, or to with the real feedstock there in place, we won't have that information anyways. So the Circular project in that way is very much appreciated, because we need to go in that direction. Right?
So the next question would even be a question for somebody else in the room. So for Marcos, who's leading this volatile fatty acid separation work package in our project. But here maybe it goes to Patrick. So the amount of acetic acid, does that justify maybe valorization of that stream? Or is it better or easier or whatever to maybe put this in an anaerobic digestion plant and to deal with that in that way?
Yeah, I think it's a really valid and interesting question, and luckily it's also something we're looking into in the project, both experimentally and for modeling aspects, if it's worth it financially. So the concentrations are around 10 grams per liter of acetic acid. The other VFAs are relatively small concentrations. Other SAF precursor technologies, when you're working with VFAs, they're typically much higher, I think in the range of 50 grams per liter or something like this, where it then gets more interesting. So the short answer is I don't know for sure yet, because we haven't finished the techno-economics of if it's actually worth it to do it. maybe it is, I think as Tina has hinted, that a biological process will have to take care of it in the end, the last 10 grams. Yeah, but the levels are 10 grams per liter. I don't know exactly if it's worth it. Possibly not, possibly yes.
Yeah. So I think we also don't go all the way to jet fuel for these side streams. The same with the methanol in our project. We see it as a final product, at least for the implementation that we are doing. But of course, you could then add a lot of things to optimize then also the jet fuel yield if you want. So, I mean, Patrick, one of the questions you can choose among your questions to Juliano, but one was touching other options to treat the hydrothermal liquefaction aqueous phase. So maybe we start with that. So how does wet oxidation compare to the other options that we have at hand?
Well, I think the other options, especially the biological ones, as we were talking just now, it is a toxic water, so it's kind of difficult for the microbes to actually get it raw and undiluted. There's some dilution going on there, and it is possible for sure. I think what will determine what is the most applicable thing for hydrothermal liquefaction will be the capex. Well, not only the capex, but the business scenario itself. So if you are not in a wastewater treatment facility, are going to build a dedicated biological treatment for aqueous phase, and that comes with its own costs and with its own reliability. At least with wet oxidation, and the way I see it, we know that it burns the toxic compounds. So to a certain extent, we are oxidizing them, and it's quite direct. Now, if you build a HTL plant that is not in the wastewater treatment facility, you make a biological treatment, and if your feedstock changes in the beginning of the HTL, how will that toxicity change on the aqueous phase actually work with your microbes, depending on the type of process that you're choosing on the microbial side, right? So for sure, something that we see as a possibility, but it should be determined what is the most optimal scenario here, technically, right? I don't know if Patrick, you see more or less that way, or?
Yeah, I guess so. I think we kind of lack larger scale demonstrations of each of these technologies. So also the biological, there's been a lot of lab stuff done, and that shows inhibition, and when you can get around it, maybe, but none of it's really been demonstrated in larger scale to any significant extent. So it's hard to say if it'll actually work. But of course, the same applies to wet oxidation, with the slight advantage that there is commercial wet oxidation technology out there, like you mentioned. So you could just, have an HTL reactor and then buy a wet oxidation reactor, and you could more or less rely on it working. So I think that is maybe, as you mentioned, maybe it's an enabling technology, because the HTL process water is obviously one of the, if not the largest challenge in commercializing HTL, I would say.
Okay.
Yeah, that's for sure.
So we come almost to the end of this webinar, and maybe Melike, you can unmute. Somebody can raise his or her hands for kind of a final question, and Patrick or Juliano, maybe one of you can take the question of IP in the chat first.
I guess the question is if the ammonium in the acetate could be used directly as a fertilizer. And I think that would be really quite nice. If you reduce your COD by 80%, you remove the toxicity, then this is certainly a very interesting aspect. We were not in this project, unfortunately, but we were planning on doing this in another project, and we've applied for some work to look at this. It's very much also depends a lot on the toxicity, residual toxicity, and if it would be viable, but it's definitely worth investigating. That would be ideal. Then you can just give it back to the farmer.
Yeah, I was going to add on the ammonium acetate that it might, it is a separation challenge. Then, if in the end of the wet oxidation, you still have other compounds, and that's basically where we are heading towards, having multiple contaminants, and how that actually affects the application of a product like that is still to be determined for sure. But it's an interesting approach, and I think it only makes sense if you are in a farm anyways, and you need nitrogen anyways in your viewed. So yeah.
Okay. So thank you, Patrick and Juliano. I don't really see then now another question, and it's 5 o'clock. It's good to also finish these things in time. So I also see that the people are not unmuted. So if we missed one of your question now for technical reasons, I'm very sorry for that. But we are also open. So I mean, we are a European Union research project, so you can address questions to us at any time via the channels like the web page and so on. So feel free to reach out. Having said this, I want to thank Patrick and Juliano again for your insights today. So I enjoyed it. Thank you also everybody for participation in the webinar, and have a great day, and see you hopefully for the next webinar of the Circular project. Goodbye.
Thank you, Tino.
Thank you, Tino.